I'm Dr. Cedar, an instructor for the Serious Games and Artificial Intelligence course. This course covers how to use game-like structures for scientific purposes, how to combine those structures with artificial intelligence, and how to build out both of those in working code. The students work as teams in a modern, agile software development environment, tackling both theoretical and very practical challenges. A big focus of the course is on the algorithmic, ethical, and system-level issues surrounding the creation of effective human-machine teams. The students not only learn how to implement modern machine learning algorithms, but also how to judge when a set of training data is good enough, when automation should be paired with human oversight, and how to reason about AI's broader impact on society and technology. The course is fast-paced, and students take their ideas all the way through the engineering process, including defining a relevant problem, collaboratively building code, fixing the code when it invariably breaks, designing experiments, analyzing data, and presenting their results. For me, this is a very satisfying group of students to teach because of their enthusiasm, technical skill, and creativity. I'm confident that these students will have a positive impact on whatever fields they go into.
Hey everybody, this is our game, Salvation of Survivors. It's an action-like game where you play as the driver of an ambulance in a zombie apocalypse. It was developed by me, Lucas, Sabrina, Alexander, and Soyoung. The problem that we wanted to address in our serious game is that with the countless natural disasters going on, from the wildfires in California to a bunch of environmental related disasters, coupled with the rapid growth of AI that's been happening recently, we were really interested in seeing if that AI could better handle those crisis situations than possibly a human operator could. We were analyzing how factors like ethics and risk play into user choice compared to a highly optimized algorithm, aka RAI, which doesn't have those factors of ethics that may play into human decision-making in those situations, and also determining what the ethical response to choices in such a crisis may be. Our target stakeholders were people who are in charge of survival responses, including paramedics and firefighters, and research ideas into how human controllers impact crisis response with factors like ethics going into their decisions compared to how an AI may have a different choice in a similar situation.
In our game, the player is an ambulance driver in the zombie apocalypse crisis, and the player's goal is to save as many people as possible in the given time. The player needs to react to the humanoid on the generated image and decide whether to squish, skip, save, or scrap. Each action takes different amount of time, which implies that taking actions that is longer may end up leading to having less time to save other humans. Necessary information, for example, the status of humanoid and the result of the action the player took, are all visible and accurate on the screen, enabling the players to easily take in information and make actions accordingly without being misled. There are 4 states of the humanoid: healthy, injured, corpse, and zombie. Although saving an injured person may seem preferable, in order to achieve the set goal of saving the most humans, we added a dilemma to the player's decision-making process by designing the injured to have a chance of turning into a zombie and killing everyone you have, possibly risking the lives of people who are already in the ambulance. As well as the states, the player needs to take consideration of the humanoid's occupations, since some classes will give the player bonuses that will help their gameplay. There are also other values that will not directly affect the gameplay itself, but be affected by and demonstrate the player's moral values, such as class, gender, and age. The player needs to take account of all these different dilemmas under time pressure if they decide to turn on the real-time feature, where as time goes by in the real world, the time left in the game would also decrease, forcing the player to make decisions quickly as possible while still considering the given information, which makes the gameplay more difficult and worthy of comparing with the machine algorithm.
So here's a quick look into a demonstration of our game. As you can see up top, I have real time on since time is ticking down as it goes on. A quick example of a decision I might make here is that we have a healthy person in front of us and obviously plenty of time, so I'll likely save them. This is a zombie, which if I saved would kill everybody inside of my ambulance, so I'll likely squish them. This is an injured person, but since I don't have that many people in my ambulance right now, I may take that chance and try to save them. It's another injured person, also a child, so I'd likely save them in this situation. So as you go on, you can see all these different situations. It's a corpse. I likely don't want to run over them. This is an injured person. Right now, I may skip them because I do not have the space for them. This is an injured person. I may also skip them here. And as you go on, these decisions compile into the very end after you're done scramming. You can see that how many people you've saved, how many zombies you killed, how many people you killed, how many zombies you saved and took in your ambulance, and how many injured people you squished in the end.
Receive rewards or penalties based on its actions. Over time, as you can see with the graphs on the right, the model learns how to maximize both its rewards and the number of people saved. Additionally, we also built a manual model which used fixed bounds to determine when it should scram, save, or squish injured people. To determine these bounds, we tested all possible values and tried each bound for 100 episodes, then chose the bounds with the greatest number of people saved.
Okay, so based on the data we collected, we observed that the manual model was the highest performing, saving the most people, about 13 per game. Next is the RL machine learning model, which saves around 11 people per game. And then last were the humans, who saved about 9 to 10 people per game. So the manual model is comparatively the best, while humans are comparatively the worst at saving the most people. Even though the manual model did save the most people on average, it also had the most variation, ranging from a minimum of 0 people saved all the way up to 27 people, which is way less consistent than the machine learning model, which has most of its saved people around 7 to 15 consistently. So based on the results, on the left here, we have the actions of the reinforcement learning model based on the humanoid. And as you can see, the injured usually squishes the injured most of the time. And this is due to the fact that injured has a small chance of being infected. So whenever an injured does turn infected, it learns to squish them because it kills everyone in their ambulance. Compared to humans, they usually tend to save injured instead of squishing them. And this is likely due to the fact that they have moral values, unlike the AI. So what we notice is that people usually have some distinct strategies. Some people completely ignore every injured. They don't want to take a chance of them being infected, or some will save the injured because they don't want to leave them to die. Sometimes age takes a major factor in their decision making, and they will sometimes save or skip kids even if they're injured. We also notice that if there are other people observing the player, they usually make more moral decisions, and that's also as they play more rounds, they try to get a better score, which usually means that they make less moral decisions. And then despite the fact that we have a real-time feature that you can enable or disable, we found that there's no really significant difference of enabling it versus disabling it. And finally, we also noticed that risk assessment is worse in humans compared to the AI or the manual model because of the fact that they usually save less people.
So our experiment raises a couple of further pathways to explore. If we were to continue, the first thing we'd like to do would be improve our reinforcement learning model. While our model did outperform humans, it still underperformed in comparison to the manual model. So in order to improve this, we could tweak the reward system in order to prioritize saving humans and perhaps injured humans, as well as adjust some of the hyperparameters in order to achieve better results. Additionally, our results raised the question of if you could embed ethics into AI. As you may have noticed, our model tends to squish injured people, even though it is killing a human. This is because our model was trained to purely save the highest number of people, a completely utilitarian ethical framework. However, the human results heavily differed, with many humans choosing to save injured humans. This is because humans value human life. So something we could consider would be adding an additional value to decrease the amount of humans squished in our reinforcement learning model. Additionally, the results also indicate additional research in discovering the relationship of ethics and decision-making in regards to AI in different fields. For example, other natural disaster evacuation procedures, self-driving vehicles, and even politics. And that is it for our presentation. Thank you.
Okay.
Okay. Welcome to Dead or Alive with AI by Team Arifnol. Our overall goal was to make serious games less like a quiz while also obtaining accurate data. Furthermore, because we decided to add complexity to our game, it was almost impossible to gauge whether or not the AI was performing well and making good decisions, so we decided to compare our model to human data. The basic premise of the game is that an apocalypse has happened, and you are an ambulance driver that is in charge of rescuing people to help start a new colony. The player will be faced with dilemmas throughout the journey as they aim for a high score in order to help the colony thrive while balancing that drive with ethical decisions. The goal is to save as many people as possible while ensuring that the colony has the skills necessary to survive. We have 4 types of humanoids. Healthy humanoids are safe to rescue. Zombies are dangerous and can only be safely rescued by using the time-costly cure button. Injured humanoids have a between 1 and 15% chance of turning into a zombie while rescued. And lastly, dead humanoids provide no benefit to rescue but are also not dangerous.
This is the main game menu. On the left-hand side, there are the action buttons as well as information about the humanoid and which types of professions the player has. The AI controls are found on the bottom, while there is info about the time and capacity of the van on the right-hand side. As the player progresses and rescues, new humanoids will appear, the time will move forward, capacity will fill up, and the profession's light bulbs will light up. We also added sound into the game to simulate a more realistic experience for each of the actions. This is the game after some progress. The HP is depleted, the time has moved forward, capacity is near full, and multiple different professions have been rescued. The game will move through a variety of different environments as shown. Next, we have conflicting variables. We introduce conflicting variables in order to create dilemmas and test human and AI decision-making. We have 2 different AIs that we implemented. This one is the CNN, or the Convolutional Neural Network AI, that looks at the image and classifies what type of humanoid is on the screen. Suggest gives the recommendation while Act executes it. We introduce uncertainty here as the AI is not always available, and thus the player has an unreliable aid and must try to work around the limitation.
We have 6 different professions and a default worker role. The player must balance their rescue efforts between saving anyone they can and trying to save at least one of each professions. This dilemma is further compounded by the violent criminal profession, as there is a 30% chance that the game will cost the player points on pickup instead of giving points, and the player must decide when they want to save and when they want to skip.
The HP bar was introduced in order to help limit the amount of times the player could use the squish button, as it is the most time-efficient option and could be abused. The player starts with 1000 HP and loses between 100 to 150 every time they squish, and squishing is disabled at 150 HP. This introduces another dilemma of when the player wants to budget their HP and when they need to go through as many options as possible. The scoring is a combination of multiple factors. These included the amount and type of humans that were saved, killed, and extra points for having at least one of the 6 different professions. Saving a zombie will result in a complete deduction of your score, unless you have scrammed previously. The score is saved by the computer each time the player scrams, serving as a checkpoint. For example, if the player accidentally saves a zombie after scramming, the score resets to the score you had the last time you scrammed.
This is the full screen that greets the player after they scram back to their base for the last time. Once the time runs out, the game gives the total count of the killed and saved. Now we would like to introduce the game scene software Unity. Unity is a game developing software that we use to generate images to add more variety to the ones in the base game. We added more humanoid assets, changed the background scenes, and used the generate character script to randomly switch the position of the humanoid. These are examples of the new alive and injured humanoids we generated through changing relative camera placement and altering the Skyblock's asset. The dark mode gives more variability in the scene and adds a dilemma if the player cannot tell who is in the picture. These are examples of the new zombie and dead humanoids we generated.
So along with the image classifier, we also wrote a reinforcement learning algorithm, and we'll go over that here. So to play the game as optimally as possible and compete against human subjects, we chose to use reinforcement learning, where the machine learns from its environment. We chose this specific model because of three main reasons. One, our base game followed a specific scoring system. Two, our game has so many possible states that labeling data is not feasible. And three, in our game, we can easily map a state to a specific action. Now I'll introduce the basic components of reinforcement learning. They are the environment, the agent, and data storage.
One of the most important parts of the machine learning program is the environment. The environment is a copy of the base game, but changed slightly to be used by the program. Rather than having a scorekeeper function, however, it rewards or punishes the AI for each action.
The agent's main job is to select an action based on its current state. Choosing an action depends on two main factors, the data table and epsilon. The data table will be explained in detail in an upcoming slide. Epsilon is inputted into the agent to tell how often its action should be randomly picked and how often it should choose the best action based off its prior knowledge. A higher epsilon value would result in a higher chance of randomizing actions, while a lower epsilon would result in a higher chance of choosing the best action. Both are important to the training process. Being able to quantify how profitable taking an action is given a state is difficult. To get around this, we use the Bellman equation, which provides a quick and easy way to quantify how good an action is. We also adapted the equation to handle adding higher dimensions so that it was compatible with our data table and found that it still worked.
The way the data for each state action pair is stored is inside a Q table, showing the favorability for each state action pair. At first, it was only 2 dimensions. We eventually added time as a third dimension onto the Q table. Our reasoning was that we could allocate 2 of those dimensions to being the state space and leave the 1 dimension left for action, preserving the table's original state versus action structure. That worked, and so we continued adding more dimensions to bring our state space to parity with the base game. Ultimately, our data table grew 7 dimensions, resulting in 6,912,000 possible data points. This is the result after even implementing some equations to drastically reduce the size of the Q table.
So as we coded the AI, we encountered a few roadblocks. We resolved our first issue by making the Q table multi-dimensional and adapting the Bellman equation to work with a new Q table, which worked. We resolved our second issue by storing a flattened version of the data table in a .txt file. For the third issue, we originally planned to have 6 different professions, but that made the data table too large. With our limited computing capability, we had to decrease the number of professions to 3, which sped up the model a lot. We solved our last issue by tweaking the reward system to disincentivize scramming unless you already have a decent amount of humanoids in your ambulance.
Here are some data we have collected from our machine learning program. On the top, we have the growth of the program, with the score increasing rapidly in the first 15,000 runs. The fourth graph shows the scores of the trained program, and the final 2 graphs are the varying scores based off epsilon values inputted to the program.
As we trained our model for more episodes, we saw differences in how the epsilon versus score graphs looked for different amounts of training runs. For example, training for 50K runs results in a sharp decrease, while training for 100K runs results in a plateau-like shape after a certain epsilon. We attribute this trend to an increasing amount of exploration. Beyond a certain epsilon, more exploration becomes detrimental to the performance, since the AI isn't getting enough training runs to discover the correct options. To compromise with our limited computing power, we capped epsilon at 0.6.
We conducted a 2-sample t-test to address our second research question, and our initial hypothesis was that humans would outperform the AI. The AI sample size was 1,000, and the human sample size was 17. We found the p-value to be 0.547, so we do not have significant evidence that the human scores are greater than the AI scores on average. As shown in the box plots, the scores seem to be pretty similar, but since these are preliminary results, future testing is necessary to draw a definitive conclusion. Having said this result, however, I do want to mention a few things that affected our data. First, we did training trials for the humans so that the learning process would not affect the data. Additionally, the reinforcement learning model trained off a slightly modified form of the game with slightly fewer professions, which created some sort of bias in the results. In the future, the human sample size should be larger in order to reduce variability, since a sample size of 1,000 compared to 17 made the AI results significantly more precise and more consistent with each other than the human results, as shown in the top graph. This slide includes histograms of the AI and human score distributions. As you can see, although the centers seem to be pretty similar, the AI score distribution is relatively normal with a distinct shape, while the human scores have somewhat of a normal distribution with greater variability. In order to verify the normality of the population human score distribution and reduce noise, more human testing is necessary.
Thanks for listening.
Hi, my name is Clark.
I'm Gabe.
I'm Shubhranshu.
I'm Ada.
I'm Chi.
And I'm Siditi.
We are Team 1 in the Serious Games with AI course, and we're going to go over our project.
Okay, so starting out, our research question was basically, in scenarios where you need to make quick decisions under time pressure, what drives the choices of humans versus those of machines? And to study this, we used a game-based approach to try and understand the sacrificial choices that individuals in AI make when faced with moral and ethical dilemmas. Next slide, please.
So to provide some context about our game, essentially the zombie apocalypse has occurred and the player is driving an ambulance looking for any viable survivors to bring back to their colony. And their decisions revolve around two basic values, utility and morale, which they have to maximize or balance to maximize their final score based on the humanoids that they encounter. Next slide, please. And so this is just like a look at the classes we have in our game. So we have specialists, which are doctors, fighters, and engineers who have high utility and high morale. And we have children who have no utility, but they add to the morale. And we decided to add these classes to compare how AI and humans work in dilemmas and making decisions. Next slide, please. And so this slide just is a look at our UI. So we have to the right, we have a remaining time, we have a clock which shows a remaining time and a capacity meter, as well as our AI bot Simon that can be suggested with the button on the very bottom, who can sometimes incorrectly suggest what the humanoid is in the screen. And then to the left, you can see the utility morale bar, which the player can use to keep track of their how their decisions are impacting those two factors, and a button panel with 4 functions and numbers that correlate with the relative time cost because there is a time constraint which each decision.
So in testing, we had several specific questions we were trying to answer, and we also foresaw a few applications of our game. One would be for first responders, trying to train them to make quick decisions. And sometimes they need to choose between two kind of ambiguous decisions. And we also can use the game to try and understand underlying human biases when put in stressful and time-constrained situations. And we can also use it to view the human perception of AI under stress. Like, will a human be willing to rely on AI that may make better decisions than them in a stressful situation? Our process, we started out using Unity to auto-generate new pictures with 7 new classes and various cluttered backgrounds to kind of make the game harder for the AI. And we also revamped the scoring system with a utility and morale score. And we also added a new feature where you can view the current occupants of the vehicle and choose to swap any one of them out for the person that you see in front of you. And finally, we also trained an RL model so that we can compare its performance against our human testers.
And one of the important mechanics that we added is swapping, or more realistically, sacrificing, where you're able to kill a person to save another. And with this, we're able to see how morality interacts with a utilitarian mindset. And it's kind of like the trolley problem where you have to ponder, is it ever worth it to kill an injured child in exchange for an engineer or a doctor who will be more valuable to your colony? Next slide.
All right, so here are our findings from our experiments. So here's our confusion matrix for our classifier, which serves as the backbone for our RL model. You can see that it is not 100% accurate. It often confuses specialists with regular humans. So its real accuracy is actually around 86%. And we applied the PPO RL algorithm for training using 2 different models, one that could swap and another that couldn't. You can see that the non-swapping model converged almost 10 times faster, which is possibly due to the differences in either architecture or action space. However, both models ultimately achieved an average score of around 38, so it seems that the AI did not benefit from the swapping feature. So seeing the final score distributions for the model and humans, you can see that despite the variance in scores for both, the model still significantly outperforms humans by a factor of almost 2.
And the reason we think that the model outperforms the humans is because we noticed that humans would typically pick up every humanoid they encountered, regardless of their productivity, only that they would later swap them out for a more productive human. This would cost extra time. And the AI, on the other hand, would only prioritize the productive humans. So rather than picking up an unproductive human only to swap them out later, wasting that time, they just skip the unproductive human in the first place. So it turns out that the AI runs with more swaps were usually the ones where it made mistakes picking up less productive humans, so it would have to use extra time to swap out for a more productive one. And that's why the AI with more swaps usually ended up, the AI runs with more swaps usually had a less score, and the human runs with swaps had more score.
So just speaking of moves more generally, this is the plot of the frequencies of choices for the model and testers when they encounter either a human or a zombie. So surprisingly, the model actually grabs fewer humans on average than our testers, and this is possibly to avoid less important ones like kids or regular humans, which have relatively low scores compared to specialists. And also it saved time by squishing humans instead of skipping them, as opposed to our human testers who almost always skipped. And for zombies, however, both the model and our testers treated them similarly.
Each time our game was played, the ambulance capacity was randomized to either 5 or 10 to see whether this would affect gameplay. On our first graph, you can see capacity versus swaps. We noticed that the runs with a capacity of 5 generally swapped more, which probably meant that they were making more trade-offs with less resources. On the second graph, score versus capacity, we can see that the runs with a capacity of 10 generally scored higher because they had more resources and they had a better ability to pick up more useful humans at once.
So I'll talk about a few more of the qualitative conclusions that we found through this project. One big thing that we found was that humans preferred actually to use their own judgments and would only use the suggest button of the AI in very uncertain circumstances where they possibly couldn't see the humanoid fully. We estimate that this is due to the fact that people generally value their autonomy and they prefer to exercise their own judgment whenever possible so that they have a sense of control over what they're doing. This does have somewhat concerning implications in the real world as we continue to integrate AI and humans together. It leads to problems where humans may not trust the AI in the future and rather look to their own judgment. So another thing we found was that testers that tested in a group, as in 3 people working together to play the game, were willing to swap out children or just people in general for higher utility scores, while individuals who play the game just by themselves rarely use that feature. We thought this could be because the players in a group felt less individually accountable for their decisions and just wanted the best outcome for the group as a whole, which meant making the hard moral decision of actually abandoning people. Additionally, we thought that the competitive environment that they were in, where they actually said that they wanted to try and get higher scores than the other teams, possibly caused them to sacrifice more and focus on that score.
Some final observations we had. The first was because zombies were identified by their skin tone. So if their skin was greener or darker, they're more likely to be a zombie. Darker skinned humans more often got confused for zombies and were accidentally killed. Another is score over morality. Like we said before, the groups of players often ignored the moral implications of their actions and instead cared about getting a better score. And this is also partially because of the game itself. It's easier to kill a kid that doesn't really add much immediate utility to the city in the game, rather than in real life, where it's much harder to kill a kid and definitely morally very questionable. Next slide.
Imagine what could be accomplished if only the human race would shed its humanity. Max Brooks. This quote summarizes kind of what we learned in our experiment and how removing emotional and biases and constraints could lead to rational and efficient decision-making processes. However, it raises ethical concerns about the consequences of sacrificing core human value and children's for the sake of progress. It is this humanity that makes us distinctly human, and it's interesting to look more into this as we integrate with AI. Next.
Thank you for listening.
And that's it. Thank you.
Thanks.
Hello, we're Team Prime, and this is our presentation. Our motivation for our research began when examples of excessive trust in AI like ChatGPT was brought up. We wanted to study how reliance on a secretly flawed AI can bring about harm, and we wanted to understand how humans trust AI to try and gain some insight into how an AI can be made more or less trustworthy. These ideas culminated in examining how trust in an AI evolves over a short period of time through a human-machine teaming-oriented serious game.
So our main research question was, how does AI performance affect human decision-making? To do this, our game revolved around the premise of players manning an ambulance during a zombie apocalypse, their main goal being to save as many humans as possible. However, if they save a zombie, the zombie will kill all the humans already in the ambulance. Each turn, the player has 4 actions: skip, save, scram, and squish, and each of these actions has different time costs. Additionally, the ambulance can only hold 9 humans, so the players have to be careful about their choices. Players are also able to prompt a suggestion from the AI model, called Simon. As you can see, the base game that we were given to work with is very plain, but most importantly, it was extremely easy for the player to distinguish between humans and zombies, without the need to ask Simon.
This is the game that we created from the base game. As you can see, we introduced new features and modified the UI to make our game more unique. First, we replaced the base game's white buttons with colorful buttons so that the player could easily identify each action. We also replaced the analog clock with a digital clock that ticks in real time to add time pressure, which forces the players to make quick decisions. The capacity UI was also changed to be in the shape of an ambulance, and we introduced the day and night cycle to add variation and make it harder for the AI to classify zombies and humans. We added random bloodstains and windshield wipers in the game window to obscure the player's vision, which encourages them to prompt the AI. The AI, however, remains unaffected by these obstacles, which makes it more reliable. Finally, we included an icon representing Simon, the AI assistant, either as a person or a robot, to check for implicit biases in the players.
For the images generated for our project and training of AI models, we implemented a multitude of changes. We added 4 new types of people in order to make classification more difficult: a man with a suit, a doctor, a policewoman, and an elderly man. There is no social value system currently implemented in our game, so saving a doctor over a common citizen is exclusively a moral choice. There is no gameplay incentive to save one or the other. There are also corresponding zombie versions of each of these people, pictured here. Additionally, we introduced nighttime and rain using Unity's particle system, and finally, we introduced new overgrown buildings that were procedurally generated and a random flash of green light that can confuse both players and AI alike. Going into the experiment, our hypothesis was that if players are given access to AI models with varying accuracy, then the most accurate model will gradually become the most trusted, while the least accurate model will lose trust and therefore be prompted less.
To test our hypothesis, our experiment used 3 image classification models: an accurate AI model, a poor AI model, and a control model with 100% accuracy that wasn't a neural network. Regardless of the model received, users were informed that they had the accurate model. We tracked the players' actions, including how often suggestions were prompted and taken. Afterwards, we surveyed the players on how well the AI performed on a scale of 1 to 5.
Both of the models used for the game were trained using a convolutional neural network with 2 layers and a batch size of 32. The poor AI model was trained to be good at recognizing images of daytime and was only trained on images from day. This led to an accuracy of 90% for the poor AI model for the day images,
and 48% for all images. On the other hand, the accurate model was trained on 80,000 images of zombies and humans, both day and night, leading to a total accuracy of 87% across all images. After comparing the performance of the two models, we observed that the poor model did badly on images from the nighttime. As the game starts in the daytime, the model gets progressively worse as night comes. Meanwhile, the accurate model does moderately well on classification of all image types. The loss function for the poor model has less variation than the accurate one. And the confusion matrix for the poor model has a lower accuracy on all images than the accurate one.
So first of all, here's the data from the survey results we got from the experiment. As you can see on the right, the perfect model was generally rated much higher than the others, while the poor model's rating was generally lower but also had a massive variation. The full model was somewhere in the middle, which lines up with the expected performances. On the left, though, you can see that the people who rated their AI a 1 out of 5 used it a lot more often than those who rated it a 2 to 5. This could indicate that these people simply had more opportunities to see the AI's failures, thus leading to a lower rating. Sorry, my bad. Here you can see how the players adapted as the game went on. For the lower plot, which shows how many players prompted suggestions, you can see that it stayed pretty consistent for all of them. However, in the upper plot, which represents the ratio of suggestions taken to suggestions prompted, you can see a pretty big difference near the end. The poor net, represented in the blue, was vastly less trusted near the end, which makes sense as its performance was designed to be especially bad during the nighttime. The full net was somewhere in the middle, while the perfect net stayed relatively high the entire time. From this data, we can see that subjects did adjust their decision-making around AI, and they were capable of doubting it and acting against it. However, they still prompted it and used it as a second opinion, even if they felt like it was inaccurate. Our original hypothesis stated that less trust would be indicated by less prompting, but that stayed mostly the same. Still, the rest of our results indicate that trust in AI isn't blind, and humans were able to adapt to the performance, even in a time frame as short as a 4 or 5 minute game.
When we worked on this project, we were introduced to several skills and strategies, including version control with GitHub, which involved using Git commands and separating code into branches. We also used Kanban boards to assign tasks to team members and keep track of our progress. Every week, we had a Scrum meeting to share what we finished and planned for the next week. We also had a code review, which allowed us to fix each other's bugs and improve the code. A major part of this project was about data collection for our experiment, so we used CSV files to log the players' actions. We also had to train a convolutional neural network for our game's AI to work.
Some interesting future works and ideas to consider are social value, such as using factors like age, job, and status. Another interesting idea is to use reinforcement learning to compare machine action to human actions. Creating a near-perfect AI model would all be better than using a control system. Collecting more human data would provide further insights into their research question. Thank you for listening.
Hello, this is Team Alpha, and we're excited to introduce to you our project that investigates human-machine teaming in a serious game environment. Given a base game set in a zombie apocalypse, we added and removed features that would help us concretize people's decisions in morally ambiguous situations.
So here's the base game. The image in the center will either show a healthy human, injured human, zombie, or a corpse, also known as a dead zombie. The zombies and corpses are identifiable by their green skin, and injured humans and corpses will be in a lying position. The objective is to save as many humans in a zombie apocalypse and avoid taking in zombies in your ambulance until time runs out.
Here's an overview of what we'll be covering. We'll start with our goals, where we'll explain what we want to test out, then our features, where we will explain what we will actually test it out, and finally our next steps.
Our goals were to improve play efficiency, test user morality, and investigate machine-player interaction. Subsequently, all of our added features sought to tackle one of these goals.
One of the major features we added was a protector and a paramedic. We wanted the player to choose between having either one or neither, because both have their strengths and weaknesses. Once they do choose either one, it will permanently remain in the ambulance until the end of the game. If the player chooses a paramedic, they will have the ability to convert a zombie into a healthy human if they choose to save. This can help increase the player's morality score, but there's a 50% success rate.
Now, if the player chooses a protector, they will have the ability to convert a zombie into a corpse with a 100% success rate. While this might not increase their morality score, it can prevent additional casualties if the player accidentally chooses to save a zombie. However, the player will have to take in the corpse that could have been spaced for a human.
As for UI/UX changes, we added intense background music to run throughout the entire game to create a sense of urgency in a real zombie apocalypse scenario, so the player would act quicker. We also added sound effects for squishing in efforts of evoking a sense of guilt to test player morality.
In addition, we implemented an image filter, which increases the red pixel values in the image if the player chooses to squish. This complicates the game because, especially in a red filter, it's difficult to differentiate between the entity's brown or green skin. This also introduces another dilemma, as the player must choose whether to continue saving or decide to scram back to the hospital, which would reset the image. However, we added additional features that might ease the decision-making process. There are 3 buttons that allow for interaction between the player and the neural network in the background, which is an image classifier. Players can choose the Suggest button, which returns the AI's recommended move, or Act button, which does the AI's recommendation. However, both of these actions each take 7 minutes away from the clock, and we added this to see if the player was able to use their time wisely.
We also added the Info button, which tells the user the state of the entity. So if it's a corpse, zombie, healthy human, or injured human. And this had a time consequence of 5 minutes. We added this because the color filter makes it difficult to determine the entity to make a decision, and this will aid the players. This was used to test how often the player seeks help from the machine and when.
We implemented a morality meter that would increase or decrease based on the actions taken on the humans and zombies, dead or alive, and how the player value scrimming. This is also dependent on the player's choice of using the paramedic, protector, or neither.
We also implemented an efficiency meter which compares the user's actions and the machine's action. The efficiency percent is the percentage of the user's actions that are the same as the machine's. We wanted to improve the readability of the game stats, so we also added game results to the end screen, which displays the player's preferences based off the user's decisions throughout the game. Although this may introduce bias, it could also be interpreted as player experience and how that affected the player's scores. Most players expected their displayed preferences.
And here is a showcase of our game.
In order to collect and analyze our data, we made a data logger which stores all of the user's data in a CSV file. This makes it easier to view and analyze the player data. This graph shows the average number of times all the action and machine buttons were chosen. Looking at the data, we can see that people most often chose the Info button over the other 2, and people also preferred the Suggest button over the Act button. We've attributed these findings to the fact that people may distrust the AI because we didn't disclose the way it makes decisions, and people prefer to receive aid from AI rather than have it take over the decision-making completely, which supports our goal of human-machine teaming. The save action was still the most chosen, which aligned with our objective. We also find that people chose to squish more often than skip, even though both took the same amount of time. This may have been because players wanted to completely eliminate the risk of having a zombie or corpse negatively impact the community.
We then examined how the efficiency and morality scores changed after each of the 9 playtests. In terms of efficiency, players were able to match about 50% of AI's decisions. We were surprised to see the initial negative scores for morality, However, we noticed a change in the slope's directions in between playtest 4 and 5. We suspect this could be because players were only informed of the moral code in the game after playtest 4. The sharp increase in morality also supports the human's ability to rapidly process information, something that might be a limitation for machine learning when it comes to adaptability.
We expected that there would be no preference between the protector and the paramedic because they both have their advantages and their risks. However, we were proven wrong when people preferred the protector. This was likely due to the fact that there was a major risk with choosing the paramedic, and people rather be certain in the outcome of their decisions. We also expected that people would be more likely to skip because we believe squishing corpses to be immoral, and squishing also produces the filter, which prohibits the view. However, people preferred the opposite, and this may have been because people believed the corpses were a threat to the community and needed to be eliminated. Since scramming takes a lot of time and ideally should only be done when the capacity is full, we expected that people may have scrammed with low capacity in their ambulance when they had a zombie in there, which would automatically kill everyone in the ambulance. Or there may have been an intense filter and they wanted to be able to see better. This was not reflected in our data and may have been due to a lack of time to strategize before playing.
However, because of the small sample size we had, our findings could be somewhat limited.
Next, here are some next steps we would like to do. First of all, we would like to train the AI to help us determine and analyze player results. We would also like to train the image classification with a red image filter. And then finally, we would like to introduce different demographics to test morality. For example, would you rather save an engineer or a doctor? Would you rather save an old person or a young person?
Thank you for
listening.
Hello everyone, we are Team First, and we are Avery, Cassie, Isaiah, Matthew, Meryl, and Patrick. So a brief overview of our presentation. First, we're going to be going over our background, which is a brief game description, as well as a research question. And then we'll go over our AI and our data analysis of how the game results connects to our research question. And then we'll conclude with a reflection and connection to a broader topic. So starting off with our background, the research question that we were planning on answering is, how does pressure play a part in game decision? So to answer this question, our hypothesis was if players are placed under time constrictions, then players will make less optimal decisions and therefore more lives will be lost.
Our game takes place in a zombie apocalypse. You are an ambulance driver who is going around the city and trying to save as many humans as possible while avoiding the zombies. This is the view from the ambulance, and there is a humanoid in frame. There are buttons which you can press that each do different things to the humanoid. This is the health bar of your ambulance, and this is the time that you have left before the day ends. This is the capacity of your ambulance, which fills up as you save more people.
The original game had 4 classes: civilians, who are people that are standing up, injured people, who are people that are laying down and they'll die if you don't save them, corpses, which are dead zombies, and alive zombies, who kill everyone in your ambulance if you try to save them. And alive zombies can be cured with serums, which turn them into healthy civilians. We also added 2 additional classes. Engineers repair health points to your ambulance overnight. Doctors require a serum to be saved, and they'll reduce the amount of people who die overnight in the 7-day system, which we will explain later.
Here is an in-depth look at the buttons that you can click. You can skip, which skips the current humanoid and brings up the next one. You can squish, which kills the humanoid in front of you but takes less time than skipping. It will also deal damage to your ambulance. You can save, which puts the humanoid in front of you into your ambulance, and you can serum zombies and doctors. You have 3 serums, which refills every time you scram, which is when you return to the hospital and empty your ambulance. We added a 7-day system in which the amount of people that you saved is kept throughout each day. Every day, a random amount of those people will die, but this chance can be reduced by picking up doctors. The HP of your ambulance is also kept, but can be increased with every engineer that is saved. We did this in order to see how players would react to having to think about the long-term consequences of their actions.
We also added a timer for each decision in order to create a time pressure for the players. If it reaches 0 before the player makes a move, then the ambulance takes damage and it moves on to the next humanoid. When the ambulance reaches 0 health points, the game ends. We added this because we wanted to see if this would have a significant effect on the player's score or their behavior. And now let's show a quick demo run of our game.
This is my score for day 6. Let's go play the last day of our game.
Save him.
Save
Oh,
him.
thanks. What do I
Squish,
what
squish,
do I
skip
do?
him,
That-
skip.
Sure.
Squish.
Squish him.
Squish?
Hurry.
Okay, sure.
Save.
Save him.
Okay,
Squish.
yeah.
Skip him. Skip.
Skip? Alright.
Save him. That's an
Oh,
engineer. Save.
engineer. Oh my gosh.
Save
What is
him.
that? Oh, okay, thanks.
Skip him.
Okay, sure.
Save.
Oh, who is? Oh, okay.
We love you, Patrick. You're
Thank
so
you.
good.
Doing great.
Thank you.
Save.
Let's go.
Squish.
Oh,
Zero.
is that a
Zero,
zombie?
zero.
Oh yeah, Zero. Thank you so much. Oh,
Scram.
Scram.
oh no,
Scram.
our thing is full. We got a scram.
Serum. That's a
Zero.
doctor.
Is that a doctor? I got a zero.
Skip.
Switch. Skip.
Save.
Oh god, I got a save.
Save.
Save. Is that a
Squish.
zombie?
Squish.
Oh, I don't have any more zero.
Scram. Scram. Scram.
I got a scram. Oh, there's no more time left. I have to scram. Alright, guys, let's see
good
how
job.
good we did. Oh
Ah,
my
good job,
gosh.
Patrick.
I got a score of 73.
Okay, so now that you have an understanding of how the actual game works, in the original game, the game also featured an AI assistant named Simon who could offer the player suggestions on what decisions to make for the next humanoid. Since we replaced the original images in the game with new and enhanced images, we had to also create a new CNN which could offer appropriate suggestions. So our initial goals in designing the AI were that we wanted to determine whether the AI is affected by additional limitations that we added, such as skipping more and squishing less in order to preserve the ambulance's health bar. And we also added distractors into each image, such as green objects, to determine whether these would confuse the AI into misidentifying humanoids. So we trained the CNN on approximately 1,000 images with an even number of each of our 6 humanoid classes, and we trained it for 25 epochs. As you can see, the accuracy of the final result was not ideal because we suspect that it has difficulty distinguishing certain types of humanoids. For example, since healthy civilians, engineers, and doctors have a similar appearance, the AI may confuse them. It may also confuse corpses with injured people since both of them are lying down.
So while we were playing our game and having the playtesters play, we were collecting data to analyze. So this is some data we got from the playtesters. So an in-person team from a different course played and they got a total of 20, while 4 players from our class but in a different group got scores of 71, 7, 36, and 56, while 3 of them ended up dying along the way. So results from us playing the game were 70, 69, 64, 69 again, 77, and 75. As you can see from this, these data points are much closer together and they're higher on average. So in order to try to see if we could lower our scores, we reduced the time on the timer by 3 seconds, and our scores became 61, 61 again, 55, 42, 59, and 71, while Matthew died, unfortunately. So here are some graphs comparing our data. So we made box and whisker plots of both the 5-second game score and the 2-second game score. And as you can see, the minimum of the 5-second game scores were higher than the interquartile range of the 2-second score, which goes to show that even though we just had a 3-second difference, it made a whole lot of impact on our scores. And here you can see that there's a great percent decrease for all of us, and for most of us it was about above 10%. And also we noticed that players appear to make less moral decisions because of the stricter time pressure, and this caused us to save fewer healthy people.
In conclusion, as we thought, the impact of a shorter decision time had an effect on the performance of the game. It led us and playtesters to a heightened state of stress and tension, and so the effect on our mind also affected our ability to make moral judgments. Some setbacks of our data were that in-person testers were playing by proxy, so they were not directly controlling the game, and so the possible delay meant that 2 seconds for them would be unreasonable. They were also obviously less comfortable with the game compared to us, the creators, and so we had less tester data from them, and they may have been influenced by other games of similar nature and brought the thought process from other games into our game, which had affected our data. And the number of people participating in each trial also varied, which meant that it could take more or less time to come to decisions. To improve our game, we plan to create more training data for a more accurate CNN, look into reinforcement learning to see if an AI can find the optimal strategies across 7 days, make better UI, such as an ambulance, make the game less quiz-like, fix the sound effects, and have shorter sound effects, and make the design for characters better and have more variety. We also want to allow the player/AI to drive themselves around the map, and we want to do more trials during the experiment. Thank you for listening.
So thought I would mention a few other thoughts I had that students you've heard, but I think other people might be interested in hearing about how we designed this course and why we did the way we did, and then hear from the students about unexpected things they learned. I won't call on everyone individually, but I'll poke the teams one by one, and somebody should volunteer and say something. So I'll say, the obvious story of this course is, we wanted to find people who were interested in going into building AI or applying AI and teach them the technical skills to actually succeed on that path, like Python programming and convolutional neural nets and reinforcement learning and those things. But the deeper story about why, the instructors and the TAs took time out of their other schedules to do a course like this was to teach the other associated skills, the kind of skills that the experienced engineers all say are really important and that they wish they'd known when they were younger. And that includes very technical supporting skills like version control and software process and coordinating a team, and semi-technical things like requirements engineering and data visualization and user interface design, and non-technical but very relevant things like designing for accessibility and ethical decision frameworks and moral philosophy. I was very pleased looking at the presentations of how the students incorporated these ideas into their projects. They're not just mindless engineers throwing technical code together. They're thinking about the problem they're solving and who's using it and things like that. So I was going to stop and let the students talk for a moment about, I guess I'll ask you either, what did you learn from the course that you were least expecting to learn from the course, or at least among the unexpected things, what are you most glad that you learned but didn't think you were going to? I will uncharacteristically call on team first, who has gotten far too used to not being first. You are honorarily now called team second, but second to none. Someone in team first want to say something about unexpected lessons? You can just speak up. You don't need to type. Otherwise, we'll move on to another team. So,
I guess something that we learned that was unexpected was I thought that this course would focus mainly on the mechanisms and code, but alongside those, we also discussed philosophical topics such as utilitarianism and various moral dilemmas, which is interesting to me.
all right, well, I'll jump on to another team, but anyone at the end, I'll let anyone jump in if they did say something. So how about Team Prime? You were very used to being last, but we'll honorarily call you Team Double Prime. You're now no longer Velocity, but now you are Acceleration. Does someone from the former Team Prime want to say something about interesting things they didn't expect?
Well, I suppose I could have seen it coming, judging from the pre-coursework on Piazza, but I did not expect there to be such in-depth discussion about morals and the trolley problem on the last day and all of that. I did find it very interesting. So I wasn't expecting that, and I enjoyed the discussion of various moral dilemmas and all that.
Yeah, and hopefully you find that practical. It's one of the things that I think is a mistake of how philosophy is often taught, is that intro philosophies are histories, which is, you know, a nice foundation for learning the other stuff, but it doesn't tell you what to do with it. And for people who only take that, then they just say, oh, philosophy is that fun little thought experiment, but I'm going to go do engineering. So it's good that we got my my friend with an actual philosophy background to come in and set you guys straight about how I'd led you astray. All right, how about team one? We'll rename you team one, but now spelled W-O-N. Someone from former team one, now team one, have something to say?
Oh, go ahead.
You can both go.
first.
One skill I learned that I didn't expect to learn was definitely having to grab opportunities for work. So like originally when we were working on our project, like as soon as someone had an idea, they would go and grab it and then just kind of execute it. And I mean, of course, we work together. Like when we encounter a problem, we'd ask for other people's help. But generally, like you have one person working on a feature. And I realized really quickly, since everyone was so dedicated, like the jobs would just disappear really quickly. And you had to volunteer yourself first to grab them. So that was something I think I'm better at now.
Yeah, that is something I noticed too. But also in this game, I really didn't expect to be learning like so much about game design. I mean, it's in the name, serious games with AI. But yeah, and also like looking at specific games as examples like Frostpunk and other things, board games too. So yeah.
Yeah, I mean, if I had no supervision from my colleagues, it would probably just be an entirely game about, or board, a course about game design. But they reel me in to keep it technical. All right, how about Team Alpha? We'll call you Team Omega, the first ordinal infinity. Former Team Alpha, someone have something interesting to say?
Yeah, just like what Gabe said, I think we learned a lot about not just games, but like serious games, like and how games could be used other than entertainment. Because before this course, I always thought that games were just like meant to be fun, but now I could see like how not only could they be fun, but they could also be used to teach simulations to help train new people and other stuff as well.
All right, how about Team A? Maybe we'll make you Team AAA in anticipation of your future AAA software releases. Someone from Team A have something?
Yeah, project management to me. I didn't expect that because each person on our team did very separate tasks, especially in the beginning before we started merging them. But all of those separate, really like skill-oriented and like each equally important task came together in the end to make a really coherent project. And it was really interesting to learn how you can combine all these different aspects into one final project.
All right. Last, well, Aleph Null, I guess we'll call you Aleph Null, the last of the power set infinities, but provably not the largest infinity. Sorry, small consolations. Someone from Aleph Null have some thoughts?
I think there's like an unexpectedly large focus on philosophy and like the ethics of like AI and stuff, which was pretty interesting, honestly, because like I kind of did debate before that. I kind of do a lot of debate beforehand, so like this stuff was like pretty good supplement for all this. And I also thought that like the project development was a bigger issue than anticipated. Like the project management stuff, like dealing with the Git and the Git conflicts was probably like the biggest headache like I've had in a while.
Yeah, on top of that, I'd say like keeping organized, making sure your Git commits have good like descriptions and you know what everybody else is doing. It was really important to have like a successful project.
All right, if anyone else from that I rushed over before has anything, we can say that. But yeah, I mean, it's a testament to just how useful it is to work in a group that we're willing to put in such effort to have like version control and team process that on the surface has a high overhead, but like an immense payoff. It's why, one of the big things humans do is form large groups. So when you're a technical human, you have to learn how to form groups too. All right. Well, I enjoyed having all of you. This was great. Really enjoyed having you in the class, engaging in the material. I was very pleased with all the projects and how you guys came together on these things and really applied the lessons. I think we'll switch back a little bit early for the other one. I think they're playing some video clips from the other piece. I saw before we switched over, there were some clips of some of your games in there, so that zombies being squished have been immortalized as part of Beaverworks history. But wish you all the best. Stay in touch on the Discord and let me know if you need a letter or anything. I was really, really happy having you all.